Well, hi everyone. We have another video here to tell you about the research that we're doing in the Ohiopyle area. This video is specifically geared towards the Ferncliff Peninsula. Ferncliff is one of the interesting natural areas in the Ohiopyle State Park, and understanding how Ferncliff formed and understanding how Ohiopyle Falls is related to the formation and the geologic evolution of Ferncliff. It's been something that people have been talking about ever since Campbell studied this area in 1902 and wrote about it and gave us some of his ideas. Let me stand to the side here. This is these are the people involved in this research. These are the organizations that are involved. I'd like to point out the funding from the USGS and the support from the Pennsylvania State Parks, DCNR, and all the folks at Ohiopyle have been incredibly helpful in helping us pull off this research. So we have a couple of students involved, and we have a short video that will tell you all about, they'll tell you about who they are and the work that they're doing.
Okay, we're here at Ohiopyle State Park, and I'm here with some students working on this project, and I'm going to have them introduce themselves and tell you a little bit about what they're doing. So I'm going to start here with Ethan. Go ahead, Ethan.
Hi, I'm Ethan Perek. I'm a MS candidate at Lehigh University, and I'm here to map all the old river cobbles that represent previous levels of the Yohigani River throughout Ohiopyle State Park.
Great, thank you. And your partner in crime here is?
Hi, I'm Adam Patching. I'm a senior at Lehigh University. I'm Ethan's assistant, and I'm here to help him collect data and organize data. I will also be trying to create an interpretive sign for the state park.
Great. And these guys are actually funded by USGS EdMap program. And part of that, of course, is teaching them how to be field geologists and make geologic maps. Now, right behind them over here is the Ohiopyle Falls itself. And it is flowing over the Homewood Sandstone, and that's part of the reason why the falls are here. As we look downstream, you can see the area that's going to wrap around Ferncliff, and this is a very steep part of the river with a lot of rapids, really popular for rafting. And as we look on the upstream part of Ohiopyle Falls, this is now the reach that is now falling into the major cascade, and this is the upstream part of Ferncliff, and this is a much more gentle part of the river ultimately, which is good for easy rafting. This big forested region in the background is Ferncliff, and we're going to show you some of the stuff on Ferncliff, including the gravels that Ethan and Adam have been mapping.
Now, the Ferncliff area is located in the heart of Ohiopyle State Park. You can see it right here. It is this peninsula of land in which the Yohigani River is flowing from the south to the north here, comes up here, wraps around the town of Ohiopyle, which is right there, wraps around this peninsula, and continues flowing north up towards Connellsville and then ultimately to Pittsburgh. And there is a large drop in river elevation around Ferncliff. And we're going to be showing you that in a couple of slides coming up. But there's such a large river drop that whitewater rafting and a lot of other water sports are very common, very popular in the Ferncliff area. Now, Campbell, when he was studying this area in 1902, was intrigued by this very tight meander of the Yohigani River. And he wondered, how did it form? And the ideas that he came up with are the most popular. And for all we know, they very well may be correct. We have some additional data that we're collecting during this study that's challenging some of the traditional ideas, but it's important to actually get those ideas on the table right now. So what Campbell would say about the formation of Ferncliff is that originally, okay, the Yohigani River was flowing north up towards Ohiopyle, and it continued flowing north without actually going around Ferncliff. So at some time in the past, Campbell envisioned that there was a ridge here between Cucumber Run to the left and Meadow Run right here to the south. And this ridge um, is ultimately going to be breached to actually make the meander loop that we see today that makes the Ferncliff Peninsula. But in the past, there was a continuous ridge here, or it's hypothesized it was here, and Meadow Run would have flowed north and met the Youghiogheny River at about the town of Ohiopyle. And Cucumber Run would have flowed also north and flowed in this valley and met the Youghiogheny River downstream of Ohiopyle. Now, Campbell suggests that perhaps something dams the river at this point. And the reason why he says that is this whole part of what is now the neck of the Ferncliff Peninsula is mantled by Carmichael's Formation, river terraces, old river deposits. And so Campbell's thought, well, the river used to flow here and it gets dammed. And if it gets dammed, he thought, well, maybe the thing that actually does the damming is ice. And you get a big ice jam. And the ice comes down, makes a dam right there. This causes Meadow Run to back up and form a lake, and causes, of course, the Youghiogheny to back up and form a lake. And you would have generated this lake in here behind an ice jam. This lake is going to fill. And the argument is that the ridge that used to be contiguous with Ferncliff gets breached right here at this red arrow. So the lake starts draining across this red arrow and into the valley of Cucumber Run, and it connects the valley of Meadow Run to the valley of Cucumber Run. And when that ice jam departs, the argument is that now the ice jam departs, now the Youghiogheny River now flows through the old valley of Meadow Run, across this ridge that's been breached because of the overflow of the lake, down the valley of Cucumber Run, and in the process, of course, forms the Ferncliff Peninsula. In this idea, this breaching of the ridge right here at this red line would represent a major base level fall in the system, right? And that base level fall would have been where Ohiopyle Falls was born. And Ohiopyle Falls, after it's born, migrates upstream to its current location. So this is one idea that explains not only the formation of Ferncliff, but also the formation of Ohiopyle Falls. And like I said, for all we know, this is perfectly correct. But we're collecting some data, and that data is, like I said, challenging that traditional notion and putting some other ideas on the table. So what kind of data is being collected, and what do we know about this region? Well, here is our most recent up-to-date terrace map of mapping out the Carmichael's Formation river terraces. This is the sand and gravel being carried by the Youghiogheny River. And you can see that this pattern of terraces wraps around what is now Ohiopyle. Here is Ohiopyle Falls, and it continues to wrap around Ferncliff. Just the overall pattern of where these deposits are is sort of mimicking the topography of Ferncliff, the topography of this big meander loop. And that wouldn't be the case. That simply would not be the case if Ferncliff was not a long-lived feature in this landscape. If it's something that was created recently by a breach right here, I don't think we would be seeing all of these terraces, because Cucumber Run and Meadow Run are not carrying the sediment that is possible to make these terraces, particularly on the west side of the Ferncliff Peninsula. These gravels and sand here that make up these terraces have a Youghiogheny provenance. And really importantly, and we're going to show you later, there are some deposits right at the very top of Ferncliff that can't be derived actually from Meadow Run or from Cucumber Run. Now, the other thing that is really interesting is that if Ohiopyle Falls formed right about in this location and has just migrated upstream to here, it doesn't explain why there's so much deep incision on this side of the Ferncliff Peninsula. And the evidence of this deep incision you can see from the two bridges that you cross when you're on the Allegheny Passage. This is the low bridge right here, and it's called the low bridge because it's only 6 meters or so above the channel. This is called the high bridge. It's called the high bridge because it's 30 meters above the channel. And the difference in elevation of these bridges as they cross the river, one here and one here, is so dramatic over such a short distance that you really get the sense that, wow, I mean, there's a huge nick point here. There is a huge steep segment of the Youghiogheny River as it wraps around Ferncliff. And so the incision, the lake spilling over in the incision would not have just been restricted to this location. It's something that's much broader that goes both downstream as well as upstream. So here are the bridges, right? So the high bridge right here, this is the downstream, and the low bridge right here, this is the upstream. And this is, of course, on either side of the Ferncliff Peninsula. And the channel looks very different in both locations. Just downstream of the falls, as you're starting to wrap around Ferncliff, and as you're going to where the old ridge that Campbell suggested was breached, is right here. And you can see that the river in this location is very rocky, starting to get very steep. Just as you get downstream of the high bridge, the channel looks like this. Lots of rapids, very rocky, very steep. This is the good whitewater rafting part of the river. But upstream of the low bridge, okay, so you go a little bit upstream of Ferncliff, the river looks like this. And here we are actually paddling the river. We're near the Victoria Bend at a place called, quote unquote, Victoria Falls. It's not really much of a waterfall. It is a rapid, but there's a lot of flat water here. So this is the middle Youghiogheny reach from Ohiopyle upstream to Ramcat. A lot of flat water. The river is much more gentle in this region. Now, I said that there's some other evidence that would perhaps suggest that we are looking at a meander loop that's actually very long-lived, that's been here essentially as long as the Youghiogheny has been meandering through this part of Ohiopyle State Park. And that evidence comes from the very top here of Ferncliff. And the very oldest terrace, the highest, oldest terrace up here at Ferncliff, has these boulders in it. Okay, and these boulders were found by Jim. And this boulder, the pebbles in here, this tells us that this is a boulder of Longrun conglomerate. And you can see boulders of both the Longrun conglomerate here, as well as boulders of Homewood sandstone. But the boulders of Longrun conglomerate must come from upstream of Ohiopyle. They are Youghiogheny River provenance, and they come from somewhere upstream where the river crosses Laurel Ridge, Laurel Anticline. Okay, there is no long run conglomerate in Meadow Run. There is no long run conglomerate in Cucumber Run. So these tributaries cannot have come down and put that long run conglomerate there. And so if this part of the channel here is an ancestral Meadow Run, the long run conglomerate can come from that. The only way that it can get there is if it came down the Youghiogheny, wrapped around, and got there that way. It's a Youghiogheny River provenance. And so that really is makes sort of Campbell's ideas difficult to reconcile. Until we find more evidence, it's going to be difficult to reconcile. Now, in order to put some ages on these terraces, we're going to have to do geochronology. And we have a student video that talks a little bit about what the students were doing out in the field, what they were collecting and why they were collecting it to do that geochronology.
Okay, so we've moved location now, and I'm going to have these guys tell you where we are and why we're here. Ethan, I'm going to start with you. Where are we right now?
All right, right here we are at a new parking lot being cut out for Ohiopyle Falls. They have graciously come and dug some holes for us and exposed this really nice soil exposure along here. And this part is important because we have all these round gravels littered throughout the hill slope all around. There's one here, here. And this is about 40 feet above the falls level, indicating that in the past the river was at this higher level and has since cut through and is now at the level of about 1,200 feet at the falls.
Right, and we've collected some samples to do cosmogenic dating here. We don't have the results back yet as of late July for this site, but at another site not too far away, we do have a cosmogenic burial age. And what is that age?
That age is at 650,000 years.
Right,
ago.
so we would be thinking that the river must be doing vertical incision at rates of something like 10 meters or so every 500,000 years. It could be a little bit faster, it could be a little bit slower, but based on that one age that we have and how high we are above the river at this point, we're looking at tens of meters per million years of vertical incision. Now, Adam, as you guys are going and doing this work, you have some tools of the trade, and what are you guys doing like on a daily basis?
Yeah, so the iPad gives us instant access to LiDAR and topographic maps. From there, we can identify potential terraces from the air and then hike out to them and investigate using shovels and rock hammers.
Excellent. And when you guys do any sampling, what are you actually sampling? Like we said, we sampled here, Ethan, but we don't have the dates back yet. What did you actually sample?
Here what we did was we took two samples. One was of the bulk sand. We just collected a bunch of sand, stuck it in a bag, and sorted it and used that. But we also collected a bunch of these round cobbles from a single layer, and we're going to get cosmogenic nuclide exposure or burial ages for all those cobbles and create an isochron and get an age out of that.
Excellent. And we're 1,240 feet in elevation now, but as if I zoom around and look back at Ferncliff, right up there at the top of Ferncliff, there's gravels up there too, Ethan, aren't there?
There are indeed.
And we tried to date those, and the dating maybe didn't work, but we were able to get an erosion rate. And what's the erosion rate up there?
The erosion rate up there is about 16 meters per million years.
Great, thank you. All right, we'll go on to the next site.
So this slide here tells, I'm going to spend a little bit of time on this slide because it tells the story of how we use the data that's collected in the field by the students to actually do the lab work and to make the measurements that take the sediment that we're sampling and turn it into an age. Okay, so how old that sediment is, when was it deposited, how old is that terrace, that terrace landform. And we start with, in order to do this, we're going to start with the fact that the Earth is being bombarded from outer space from cosmic rays. They're generated in deep space by supernova. They come down and they interact with the Earth's magnetic field, and they get funneled through the atmosphere. And we know the production rate. We know the flux. We know the flux of cosmic rays that are coming and intercepting the Earth. And those cosmic rays come down through the atmosphere, and they interact with rocks and soils at the Earth's surface. Okay, and so there are target minerals like feldspar and quartz and calcite and olivine. And the one that we're interested in using in this study is quartz. These cosmic rays come down. We know the flux of the cosmic rays as a function of latitude. They interact with quartz and they generate elements that would not be there otherwise. In particular, they generate beryllium-10 or aluminum-26. Now, both of these isotopes, an isotope of beryllium and an isotope of aluminum, are radioactive. And we know something, not we know something, we know a lot actually about the production rate because we know the flux, we know the production rate, how fast these elements are being made in quartz at the Earth's surface or in quartz here in the soils. Okay, they're radioactive. So we have a production rate and we have a rate of radioactive decay. And so this master equation that you can see up here has a couple of terms in it, and it looks nasty, but it's actually relatively simple. It says that the amount of a cosmogenic element, such as beryllium-10 right here, what you could measure in the mineral is equal to the amount of beryllium-10 that that mineral had before it was exposed at the Earth's surface. And typically that number should be 0, but it doesn't have to be. We call it inheritance. Okay, so it's the inheritance times the decay of that beryllium-10. And in this case, the decay of the beryllium-10, this is the time term, right? So the amount that you measure is equal to the amount that was there to begin with times the decay, plus what you're producing because of more cosmic rays coming in, times essentially the erosion. So there's a couple of terms here. There's what you measure, there's time, there's the production, and there's erosion. And the two unknowns in this equation that you just can't know independently is you can't know the erosion rate, and you cannot know the amount of time that the beryllium is being produced by these cosmic rays hitting the quartz. Those are the two unknowns. So you now have to make a decision. Okay, when you go out and it's easy enough to make this measurement. It's easy enough to collect the sediment. It's easy enough to go to a lab, as here we go. Here's the lab at the University of Vermont where our students go to make these measurements. It's easy enough to do that, and it's easy enough to generate this number right here. Okay, pretty straightforward. But in order to solve this equation, you have two unknowns. You have an erosion rate, which is going to take beryllium away, and you have the amount of time, right, that you've been both producing the beryllium and it's been decaying. You have one equation, you have two unknowns. So you got a problem. So what you have to do is you have to make some assumptions. And here is Jim with another student from Lehigh, Mike Simino, and we're at Jim's favorite outcrop. This outcrop is called Turtlehead Rock, Turtlehead Bog. And Jim will be telling you all about that in one of his videos and as part of our field conference. And this gives you a nice illustration of the assumptions you have to make as to how you interpret these numbers. So at Turtlehead Bog, what I could say is, okay, I think that there's no erosion going on at Turtlehead Bog. I think that this rock outcropping here, the Turtlehead, has been exposed. It was not, it was buried. Then it got instantaneously exposed. And since it's been exposed, there's been no erosion on it. And the only thing that's been happening is it's sitting there and it's getting dosed with these cosmic rays. The beryllium is accumulating according to the production rate, and it's decaying away according to its decay rate. And so the inventory or the concentration of beryllium that I see in here is only because of production and decay. There's no erosion. So over here, you take this part of the equation away, erosion is 0. You take this part of the equation away, and you can solve that equation for an exposure age, assuming no erosion. And when we do that for Turtlehead Bog, we get a number of 202,000 years. 202 plus or minus 17,000 years that this thing would be exposed, assuming no erosion. Now, we can solve this problem the other way. We can say, well, actually, I have no idea how long this thing has been exposed. I don't know the time at all, but I'm going to assume that the number of beryllium atoms that I measure represents steady state erosion. In other words, I am zapping it with cosmic rays. I'm building up beryllium-10 at a known production rate. It's decaying away, and it's also eroding. And I don't necessarily, at first, I don't necessarily know what that rate is, but I'm going to assume it's steady state. It's come to balance with the erosion that's occurring, the production that's occurring, and the decay that's occurring are all in balance with one another. And if I make that assumption, I don't know how old it is, but it would say that the steady state erosion rate is 3 meters per million years. Okay, so this gives you some way of taking one equation with two unknowns, making some assumptions, and solving it for a long-term steady state erosion rate or a zero erosion case in which you get an exposure age. So these are the data that we actually got for Turtlehead Bog, and it illustrates the technique that we use to show you the numbers that I'm going to show you in just the next couple of slides. Now, the other thing you can do with cosmogenics is really remarkable, I think. Well, it's remarkable. Everything you do with cosmogenics is pretty cool. But we can do another interesting thing with cosmogenics if we're willing to spend a little bit more money and actually measure two nuclides. So in this case, instead of just looking at the beryllium, we could measure beryllium and we could measure aluminum. Okay, because the aluminum is also made in quartz. Now, this costs twice the amount of money, right? Because you have to do twice the amount of analyses. But for a sample, for example, that is buried deeply, and in this case, it's buried by 4 meters. I'd love for it to be buried more deeply. I'd love for it to be 10 meters down. But, back in the fall of 2019, we were doing field work right in Ohiopyle. Here's the town of Ohiopyle. This is the new parking lot for the visitor center. And before they did that parking lot over, big holes were dug. We had several meters of Carmichael's formation that was exposed. And I said, wow, this is a great opportunity to collect a sample down here deep, and we can measure beryllium and aluminum, because if you could measure both beryllium and aluminum in a sample that is deeply shielded, you can say, well, the beryllium was made at a constant rate and it is decaying at a constant rate. The same is true for aluminum, but those rates aren't the same, right? Aluminum is made at a different production rate and it decays at a different rate. And so now I have, for this equation, two unknowns, but I have two nuclides, right? And so you remember back from high school math, two equations with two unknowns, I can solve both of those equations and get my unknowns at the same time, right? Simultaneously. And so in this case, with the two, I'll get both a burial age and I'll get an erosion rate with this double measurement. So we've actually done this for a sample that we took from the site here in the parking lot. Now you can't see this anymore, but Carmichael's formation is still exposed in one far wall of the parking lot, and it's exposed right here in town. And the students made a little video that tells you about where you can actually go to see those exposures in Ohiopyle.
All right, so here we are in downtown Ohiopyle. One of our best exposures of the Carmichael's formation is here under the Bittersweet at the Falls espresso shop. At least they haven't been doing any hydro seeding here. And you could see right here, we're right at the terrace tread. Now these terraces are pretty thick. We think they might be in some cases over 10 meters thick. And we can see the top of the terrace here with kind of a yellowish brown soil in it. And we walk down the hill, and this hill is walking right towards Main Street in town. We're walking down through the terrace, and you'll see that you could see more gravel exposed right there. Gravel as far down as one can see, right? And We're going to walk all the way down to the stop sign. At this point, we lose, you can see gravel in the hill slope, and we lose exposure until we come right down below the tree, and we see more gravel again. So again, the point being that we have some pretty thick deposits here at Ohiopyle, and one of the questions we're trying to answer is why are these deposits so thick, and where does all the sediment come from? So this would be the same terrace that Ethan and Adam were talking about. We think might be about 650,000 years old, but we have some more dates coming to confirm it.
So if we put this all together, this is where we now stand. This is what we now know, and this is the conclusion of this video. If you put this all together, what you find is that the deposits here at the parking lot, we think are about 400,000 years old. And the deposits downstream of Ohiopyle that we dated back in 2018 are about 600,000 years old, 650,000 years old or so, crudely. And so if you do the math, this is the same terrace. Okay, this red terrace here, crudely about 400,000 years old. This red terrace here, crudely about 200,000 years old. If you look at the distance between those 2 points, following the Youghiogheny River around Ohiopyle, around Ferncliff, ignoring for a moment the Campbell idea of how Ferncliff formed. If you follow that, that's about 2.5 kilometers distance. And so we would say that this terrace and that terrace are the same. Okay, it's the same terrace, but the age is time transgressive. This guy is older than this guy because this terrace is actually being formed as this nick point, as Ohiopyle Falls is migrating through the system. Okay, if Ohiopyle Falls was actually way downstream here on the other side of the High Bridge, and Ohiopyle Falls has been migrating upstream, it explains a number of things. It explains why there's so much incision beneath the High Bridge and so little incision beneath the Low Bridge, because Ohiopyle Falls hasn't gotten there yet, right? When Ohiopyle Falls gets to the Low Bridge, there's going to be the same amount of incision beneath it as there is at the High Bridge. It just hasn't gotten there yet. And if the migration of Ohiopyle Falls through this reach is incising, making the valley deeper, and abandoning the floodplain of the Youghiogheny River, well, it abandoned the floodplain down here 600,000 years ago, and it abandoned the floodplain up here about 400,000 years ago. And if we look at this distance, 2,500 meters in about 200,000 years, we get a retreat rate of 1.25 centimeters per year. That Ohiopyle Falls is moving at about 1.25 centimeters per year. Now that number is on the low end of the numbers that I was reporting in the other video about our work around the Ferncliff area. And like I said, these numbers are very fluid because the data, the geochronologic data is just coming in. You can see some other numbers on here, including the erosion rate for those long-run conglomerate terraces, long-run conglomerate boulders at the top of Ferncliff right here, about 13 meters per million years. You could see that we have a retreat rate for Cucumber Falls based on 2 exposure ages, one just upstream of the lip of the falls, one downstream in the gorge below the falls, and we would get a retreat rate for Cucumber Falls of about something less than 0.5 centimeter a year. And you might say, well, why would Cucumber Falls be going more slowly than Ohiopyle Falls? Well, there's a lot less water going over Cucumber Falls. And with less water, that waterfall can't get pushed back any faster. And so, in fact, this makes a lot of sense. Cucumber Falls is going more slowly than Ohiopyle Falls because there's a ton of water going over Ohiopyle Falls, and that nick point is retreating quickly, and there's much less water going over Cucumber Falls. It's going more slowly. This work is all preliminary. We've got a lot to think about, but the terrace map is pretty interesting. The geochronology is pretty interesting. And maybe next year when we're in the field together, we'll have final numbers with real uncertainties on them, and we'll have this paradox of the formation of Ohiopyle Falls and Ferncliff all worked out. Thanks a lot for listening. Hope you enjoyed it, and hope you're enjoying the virtual conference.